right? Yeah. Great. Thank you. So welcome everyone to a new episode of the C2QA Colloquium. It's really great to welcome Ash Clark as our speaker today. He is joining us from the University of Chicago, more specifically from the Pritzker School of Molecular Engineering, where he's been a professor since 2017 and is running a very successful theory group there. Just to give you a little bit history, Ash received his PhD from Cornell in 2001. He worked with Vinay Ambegowka there, and then spent 3 years at Yale as a postdoc before becoming a professor at McGill University, where he was for quite a few years, namely until 2017. Ash is at home in circuit QED, quantum optics. He's done pioneering early work on quantum optomechanics, but he's also very versed in condensed matter and many-body and non-equilibrium physics. So he's one of the few people in sort of superconducting qubits that I know who also knows a lot about Keldysh and Green's functions, which is great. He's also famous for a review of modern physics on quantum noise measurement and amplification, which I will never forget because having been a postdoc, that paper was sort of the, if you had a question, chances were that the answer was in Ash's review. He's received a number of awards, including the 2015 Rutherford Medal in Physics, that was from the Royal Society of Canada. He has a Sloan Fellowship, and much more recently, he was awarded a Simons Foundation Investigatorship and or Fellowship rather. I've learned kind of moving to this country that there are no problems, there are only opportunities, and so accordingly, Ash will talk to us about opportunities as well as good surprises in correlated quantum noise. Ash, the floor is all yours.
Great. Start the screen sharing. Hopefully you can all see that. Thank you so much, Jens, both for the invitation to speak at this online colloquium. Also the very, very kind, overly kind probably introduction. Just in case someone was worried, there will be no Keldysh Green's functions during this talk. So, hopefully you don't tune out right away. Yeah, so as Jens said, the title of this talk is Correlated Quantum Noise, Surprises and Opportunities. I want to tell you about two recent results, two recent stories that I think are fun for sort of different reasons. These are both topics that have a kind of applied aspect, so things that we think will be useful for quantum information processing, but also touch on some kind of, I would say, fundamental issues. So the first thing I want to tell you about is some surprises in the most basic kind of spatially correlated noise you might encounter in quantum information. So a bunch of qubits experiencing some kind of correlated dephasing noise. I'll try to tell you there are surprises already in this setting that this kind of correlated dephasing can be surprisingly quantum in nature, really different from what you could get in a classical model. And on top of that, oh, is there a question or a...
No, this is different. I don't think you know this. Huh? Alex said this? Oh, you got C2QA.
I think somebody needs to mute their microphone, please. Yoon Zhao.
Oh, sorry.
I thought someone was already objecting to my first slide. That hasn't happened for a long time, right? But I do remember those days. Another story. So this first story, correlated sort of dephasing noise, can be surprisingly quantum. Also connections to some physics that at first glance seems completely different. Connections to time reversal symmetry, entanglement generation, connections to something that sounds really exotic, non-Hermitian dissipative Ising interactions. So that's the first thing I want to tell you about. The second story, again, time permitting, turns to noise that's correlated now not in space, but in time. And this has to do with a single qubit that's driven by non-Markovian noise and also driven. And here the question is there a good way of modeling this kind of situation, a way of modeling this kind of dephasing, this kind of noise that is maybe simple to implement and leads to physical intuition. And so we think we have an interesting new way of approaching this, and I'll try to give you a sense of that. So let me start by acknowledging the people who actually did the work. This first story on spatially correlated quantum noise was really led by a former postdoc who's now at IBM, Alireza Saif, also involved a grad student in my group, Yuxin Wang, who will be graduating this year and looking for a postdoc. And the second story I'll tell you about, modeling non-Markovian noise, this involved Alireza. It was led by, again, a former postdoc, Peter Grozowski, who's now at Oak Ridge. And our host, Jens Koch, was also involved in this work. Okay, so let's launch into this. And again, because this is a colloquium, it's nice to start from a bird's eye view of the general kind of problems we're sort of thinking about that I'll be telling you about. So often in quantum information, we're trying to understand at some level a cartoon like this. So we have some system, maybe it's a qubit, a collection of qubits that we want to do interesting things with. They're described by some Hamiltonian, but those useful degrees of freedom are coupled to all sorts of other stuff, right? We can't control things that typically degrade the performance of our nice qubits, our nice degrees of freedom. So we have this generic system where there's a system, it's coupled to some environment or some bath that has its own Hamiltonian, they're interacting in some way. And often what we want to do is we want to come up with effective descriptions of this typically kind of messy situation, effective descriptions that will let us understand the emerging dynamics. So often we want to think of this situation in a way that's akin to how we would think about dissipation in a classical picture, right? So in a classical picture, we might think about part of the effect of the bath of the dissipation is it's driving my nice quantum system, my qubits, with noise, some stochastic time-dependent field. And then maybe we also have dissipation, the tendency for things to damp away, for energy to leak out, right? And we'll have some effective description, some equation of motion for the density matrix of our system. So the kind of very, very general things we could ask, well, the first thing is, if we want to be able to mitigate the bad effects of this bath, the bad effects of the noise, we really need to understand its properties fully, right? We want to understand, does this noise generated by this bath, is it really like having classical noise, or does it have some truly quantum features? What are those quantum features? How do I deal with those quantum features? How does this noise and dissipation, how does it interplay with some external driving that maybe I'm doing to my qubits? And maybe even in a more grandiose way, does this noise and this dissipation, do they have to be bad things, right? Are there ways that we could actually use these non-unitary elements of how our system is evolving as a resource? Okay, so that's the really, really broad setting for the two stories I'm going to tell you about. I think often when I tell new graduate students that my work involves quantum dissipation and noise, they get kind of depressed because it seems like, oh, wow, there's all this beautiful unitary physics here. And you study how it goes away when you add all of this junk associated with the bath. That sounds like someone's got to do it. I don't want to do that, right? So I also want to at least give you a taste that there are other reasons to be interested in quantum noise besides the fact that maybe we don't want it to be there. Often studying quantum noise and quantum dissipation can reveal basic phenomena that would remain hidden, right, if we didn't look at these kinds of quantities. And so just two kind of short examples that I really like where noise really reveals something interesting in a quantum setting. So what's shown here is a little picture depicting a really famous Gedanken experiment that Einstein described way back in 1909. So this is a time where people were still, not sure, is light a particle, is a wave, is it something else? So in this thought experiment, Einstein imagined a cavity that's filled with thermal radiation, thermal light. There's a mirror that's been harmonically suspended, so it can move back and forth, and it's being kicked around by the thermal light in this cavity. So the fact that light has momentum, can exert forces, this had been known since the time of Maxwell. So what Einstein basically did was derive what we would now call a Langevin equation. He said, well, look, there's a kind of noisy force that will kick this mirror around. So that's this term in this equation of motion for the position of the mirror. And through a really ingenious calculation, he used the Planck formula to figure out the statistical properties of this noise. And he could show that this noise, right, has a term that both corresponds to particles just bouncing off in discrete units off the mirror. It also has a term that we'd associate with having random waves. Okay, so really, really beautiful example where looking at noise, you could immediately see the complexity and beauty of sort of wave-particle duality. Okay, really different example, but again, noise revealing some interesting fundamental physics. We know in a lot of condensed matter settings, we have strong interactions between our electrons. The right degrees of freedom to think about are not the electrons. It's actually some kind of quasi-particles that have been dressed by the interactions. Often these quasi-particles have a charge that's very different than E, the charge of an electron. So a really kind of interesting way of getting at what is the charge of our quasi-particles is to do a transport experiment. So run a current where these dressed electrons are trying to be transmitted through some tunnel junction, and then look at not just the average value of the current, but actually look at the fluctuations of the current. Okay, so the fluctuations of that current, right, there's a shot noise contribution that comes from the discreteness of the charge carriers that can directly give you the charge of those quasi-particles. And in the fractional quantum Hall effect, where we have fractionally charged quasi-particles, this has even been done experimentally. Okay, so all this is to tell you that thinking about noise, yes, it's something we have to do if we want to make progress in quantum information. It's also an interesting way of getting new insights into quantum phenomena. And so the two stories I want to tell you about that are focusing on correlated quantum noise, either spatially or temporally, they sort of have both aspects to them in terms of the stories. So there's both a kind of practical aspect. There's also, I would hope, a kind of more fundamental aspect that they're going to reveal some interesting surprises about the relevant quantum phenomena. Okay, so let's launch into it. The first story I want to tell you has to do with correlated dephasing noise in a collection of qubits. And again, the idea that correlated noise is important in quantum information. This is something that is definitely very timely and topical. I think many of you know there have been some really, really interesting and important experiments recently in the field of superconducting circuits showing that correlated noise does seem to be a problem. So this nice experiment from Robert McDermott's group at Wisconsin, a nice experiment from the Google group, showing that there seem to be correlated noise that causes correlated drops in the T1 times of different qubits. There seems to be correlations in the charge noise, right, that these different qubits experience. Okay, and why do you need to worry about this correlated noise? It's been known for some time that if spatial correlations of noise are strong enough, this is a problem for conventional ways of doing quantum error correction. So these are some early works pointing out that the surface code has issues if you have sufficient spatial correlations in your noise. Noise correlations, if they exist between different qubits, don't have to be a bad thing. Maybe they're actually a resource, right? Maybe we can use those correlations to fight the effects of noise. So this leads to the whole idea of spectator qubits. So the idea that if I have a collection of qubits that are all sort of seeing the same noise, maybe I can use some of those qubits as sensors, right? Measure what these noisy fluctuations are doing and use the information that those sensors give us to actually correct the information that's stored in data qubits. Okay, so this kind of correlated noise, there's evidence in certain settings it definitely exists. There's a possibility of using it as a resource. So I'm going to focus on some very, very basic aspects of correlated noise in the simplest possible setting, purely dephasing noise. Okay, and so to set the stage for that, let's just start with a single qubit, and let's think about the simplest way that classical noise could dephase my single qubit. Okay, so what do we have here? Here's my qubit. It's coupled to some classical noise that just causes the frequency of the qubit, its splitting frequency, right, to sort of randomly oscillate. So this Z is the sigma Z operator of the qubit. The qubit's Hamiltonian is just sigma Z. This is just some classical time-dependent function. So we're going to take this to be a random function of time. It's going to be 0 on average. And we're also going to pretend that it's Gaussian. So all we really need to know is this 2-point correlator. How is the noise at different times correlated? And the simplest thing we can imagine is we have white noise. So there is no correlations at different times, right? There's just a single parameter gamma here that tells me the strength of this noise. Okay, so what does this dephasing noise do? The qubit splitting frequency is now wobbling, right? If I start in a superposition state, the phase of that superposition will be scrambled. So this off-diagonal density matrix element, right, will pick up a random phase. So if I average this density matrix element over the fluctuations of this noise, I will get some exponential decay determined by the strength of the noise. I could equivalently describe this dephasing with this Lindblad master equation for the density matrix of the qubit. So this is describing the evolution of my qubit density matrix averaged over this noise. And I get this standard, what we call the Lindblad form for the master equation. So here again is my qubit's sigma Z operator. Here is the strength of the noise. So this is really just another equivalent way of describing this very, very simple kind of exponential dephasing. Okay, so this is all coming from classical noise. If I had a quantum bath, so my qubit couples to some bath, the bath operator is B, maybe it's an infinite collection of harmonic oscillators. In many, many limits, we'll end up with exactly the same description. If that quantum bath has a sufficiently flat density of states, we'll again get this simple Markovian exponential dephasing. So that's everything you need to know about one qubit dephasing in this simple Markovian limit. Remember the definition of this dissipative superoperator. It's going to show up again. So what about many qubits, right? And many qubits that are now still driven by classical noise that maybe is correlated between the different qubits, right? And so now I have n qubits. They each have a Z operator, Z sub j. Each one is driven by some classical noise. And now again, we're going to take things to be Markovian. So these noises are 0 on average. But now maybe the different noises are correlated with one another. So before we just had one number to characterize the noise. Now we have this covariance matrix. So this n by n matrix V that has to be real and symmetric that basically tells me both how big is the noise on a given qubit, that's the diagonal elements, and also is the noise on qubit 2 and qubit 5, are they correlated, right? So those are the off-diagonal elements. And again, this situation here is completely equivalent to this master equation now for the density matrix describing our n qubits. And again, we see it has the same structure. There are only Pauli Zs showing up here, right? This is still just dephasing. All of the correlations of the noise, right, are showing up in these coefficients, right? So what's a nice way of thinking about this? If you see some, real symmetric matrix, you should probably diagonalize it and life will become easier. So the same thing is true here. If I diagonalize this matrix, I'll get a set of positive eigenvalues, gamma tilde j, some real valued eigenvectors, vj, and I can equivalently think of this problem here, where each qubit sees some noise that's correlated maybe with the noise on the adjacent qubits. I can think of it as this way, right? So I can think of having n independent noise sources, right, corresponding to the eigenvectors of this matrix. And each one of those independent noise sources is possibly coupled to all of my qubits. So here I have just 3 qubits. So that leads to this sort of picture. Here are my independent noises, still white noise, right? But now the etas are not correlated with one another. These vectors V tell me how does each noise source couple to the different qubits. And this is just a vector of Z operators, Z1, Z2, Z3, okay? So this is how we would think about spatially correlated classical Markovian, dephasing noise, right? Again, I could rewrite this master equation in this form. right, using the diagonalization of V. And again, I have n different terms for these n different noises, n different dephasing rates. And these V's here tell me how is each noise source coupled to the different qubits. Okay, so where are we? We, I think, now understand the basics of classical correlated Markovian dephasing noise. This can still give you some interesting physics, right? So now if we have these correlations, the dephasing rates on my qubits are not simply additive, right? Just knowing about how a single qubit superposition decays doesn't tell me how some entangled state might decay. This kind of classical correlated noise could generate classical correlations between my different qubits. But one thing it can never do, this classical noise can never generate entanglement, right? Because at the end of the day, before I average over the noise, each qubit is just being driven by its own random magnetic field. Just classically correlating those will never generate entanglement. Okay, so we have everything we could possibly say about this simple classical correlated sort of dephasing problem. On some level, you might think this is like the world's most boring master equation. We've got a bunch of qubits, but look, everything commutes with everything, right? We only have Zs here. We typically think quantum mechanics only gets interesting when things fail to commute. We don't have that issue here at all. So let's try to make this equation slightly less boring. Okay, it's still going to be boring. We're still just going to have n qubits. The dephasing dynamics will only involve sigma z's. So all the operators on the right-hand side here will commute. Let's make things more interesting by just changing this matrix V a little bit. So what if this matrix V now is allowed to be complex, right? Does that really change anything? And again, the master equation at first glance looks just as boring, right? Everything commutes with everything. So the first thing is, as long as this matrix V is still Hermitian and positive semi-definite, right? It's allowed to be complex. This is a completely valid quantum master equation. It maps physical density matrices onto physical density matrices. This is an allowed evolution, right? We still have just purely dephasing dynamics, right? They're only sigma z's. The prize is, and I'll explain this in more detail, is
one second.
I'm
going to remind people to please mute yourself. But then there's also questions now that just came in through the chat. So number one, when you talk about master equations, you mentioned Lindblad form and how it can be derived if the spectrum is the spectrum/density of states is flat. How can you understand flatness and what will happen when it is not flat? That's question number one.
Yeah, so the way I'd want to answer question number one is stay tuned for part 2 of the talk, right? So part 2 of the talk is all going to be about worrying about the fact that, you know, in the classical picture, I could imagine noise being correlated at different times. I'm throwing all that away right now. In a quantum picture, I could say, look, my density of states, right, spectral function, if you want to call it that, is not completely flat. All of these things are, in general, going to lead to what we would call memory effects. The fact that the most direct way of thinking about the dynamics, how does the state of my system change at time t? I kind of need to know what it was doing at earlier times. That is the biggest thing you're going to have to worry about. And in the second part of the talk, I'm going to propose a maybe friendly way for how to deal with that problem. Here, what I'm trying to convince you is these are all great questions and important things. Even if you throw that away, there's something still non-trivial that's left when we think about many qubits. And I think for us, this was a bit of a surprise because you might think, oh, look, if everything is Markovian, right, I don't worry about correlations at different times. There can't really be all that much interesting that's left to happen. And what I'm trying to convince you here, and I'll continue with, is in this many qubit Markovian dephasing problem, we can have surprisingly quantum effects. But yeah, I'll get to that more in the second part of the talk. Yeah.
Thank you.
Question 2. Bikun has a question asking, what is the difference between spatially correlated Z noise versus multi-qubit noise given by a ZZ operator, so product of two Z's acting on two different qubits.
Yeah, and that's going to add even more richness to the sort of story here, right? So one way of thinking about it is, one of the key points I wanted you to take from this slide was, in this setting, if this V is real, this is always equivalent to driving with classical noise. It's like driving with a Hamiltonian like this, where these coefficients are random. So every qubit is seeing its own independent random magnetic field. This can never generate entanglement. So if I now had a generalized master equation where maybe on the left-hand side here, there was a Z1, Z2, well, in some cases, that's also equivalent to a random Hamiltonian like this, but now it's like a random interaction, right? So we know that if I have some time-dependent interaction between two qubits, that could generate entanglement. That could still generate entanglement, even if the coefficients were fluctuating. So in that case, right, I wouldn't be surprised that even classical noise, it's like classical noise that is really coupling in a very non-local way. It's modulating an interaction between the two qubits. That could generate entanglement. This is really like saying I have noise, it's just magnetic fields on the different qubits and they're correlated, right? So if I think about the underlying, let's call it stochastic Hamiltonian, there's no interaction here at all.
Great, thank you.
Cool, okay. And yeah, the questions are great. I think it definitely, it convinces me at least. There's an audience on the other side, so that's always good. So what I was telling you is I'm making this equation slightly less boring by making V complex. This is still a legitimate master equation. It's still Lindblad. It doesn't, cause a disaster with our density matrix. But now I'm going to try to convince you this is not equivalent to driving with classical noise, right? And again, one thing we could do is I could say, well, look, this matrix V now is complex Hermitian. I could diagonalize it, right? It has some eigenvalues, some eigenvectors. I could rewrite the master equation in terms of those eigenvalues and eigenvectors. This is what I get. This is my Lindblad dissipative superoperator. But now this vector V is a complex vector, right? So I can't think of, oh, these are, each term is like an independent noise source. This vector is telling me how that independent noise source is coupled to each qubit, because this vector V is complex, right? So the question is, how exactly then do we think about this kind of more general setting? When do we actually have to worry about this more general setting, given some underlying physical model? I think that's the two questions that I have here. And I'm going to try to give you answers to sort of both of these questions, right? But the first thing to realize is it's still a pretty boring looking master equation. We've had a minor little tweak here. We've let V be complex. We now get something that's not equivalent to classical noise. Okay, so let's look at a simple example and let's really try to convince you that, okay, this is really going to do something qualitatively different from what classical noise could do. So here I have a single dissipator, right, where this jump operator is the sum of the sigma z's for my 3 qubits, right? But now I have some complex coefficients. So if I tried to write it in this form, if I expanded this out, I'd have a 3x3 matrix. The off diagonals would be complex in general, depending on the value of theta. If theta is 0 or pi, right, the V matrix here would be perfectly real. This is just classical noise. If it's not 0 or pi, it's not classical noise, right? So how do I know that it's not classical noise? Imagine I start with my 3 qubits in a pure state, where they're in the plus state. So in superpositions of the 2 Z eigenstates. So no entanglement, this product state. I let them evolve under this generalized dephasing dynamics, right? And what do I see? Here's some measure of entanglement. I'll tell you more about that. This is the logarithmic negativity. How entangled is qubit 1 with qubits 2 plus 3, right? And the funny thing you see is this dephasing dynamics, right? As long as theta is not one of these special values, it's able to generate entanglement, right? At some intermediate time, There's a peak here in the entanglement. It's non-zero. It depends on the value of theta. This, in terms of something much more concrete, tells us this could not be due to just driving the 3 qubits with classical noise. Something more is going on here, even though the structure of the master equation looks almost the same. This also lets us do something kind of nice, like we could spend the next half an hour or 2 hours arguing about what makes a bath quantum. What is quantum dephasing noise versus classical dephasing noise? I would argue that this gives us a very, very nice operational definition, right? Classical dephasing noise can't generate entanglement if I start with a product state. If I have a dephasing bath, and this is a dephasing bath because I cannot flip the state of my qubits, if that's able to generate entanglement, well, I should really think of this as a quantum bath. Okay, so upshot, if the V's are complex, we have the possibility of this dephasing dynamics generating entanglement. The story gets more complicated, right? Just because the V's are complex doesn't mean that we necessarily will get entanglement. So I've talked about this example with 3 qubits. If the theta is not 0 or pi, we can generate entanglement. What about this example? Just 2 qubits, right? R here is some real valued coefficient. This in general will give me a 2 by 2 V matrix, right, where I have something complex. So this is not equivalent to classical noise because there's a complex element in V, but this will never generate entanglement. Okay, so now it's even more complicated. If V is complex, it's not classical. Sometimes it generates entanglement, sometimes it doesn't, right? So there's a bunch of natural questions here. What exactly is going on? Why do we sometimes get entanglement, sometimes not? How do we think about what the extra quantum ingredient is in these sorts of master equations and why they actually can generate entanglement? Again, I'll give you a couple of different ways of thinking about that. One interesting way of thinking about it is, in general, look, there's some bath that led to this master equation in this Markovian limit. This bath is not just driving each qubit with noise. We should also think about the bath mediating interactions between the qubits, right? And because the only things showing up in this master equation are Zs, right? The only kind of interactions we can have are Ising-like interactions, so Z-Z type interactions. So I think we all know how to think about a Hamiltonian Ising interaction. So this is a Z1, Z2 interaction between 2 qubits. In terms of equations of motion, right? What's a way of thinking about that? Well, each qubit sees a Z magnetic field that depends on the Z value of the other qubit. So X1 will process in this Z magnetic field created by qubit 2. Same thing with qubit 1. Okay, so this is like a Hamiltonian Ising interaction. What's going on in one of our funny master equations where, again, we have complex coefficients in the V. If I write the dissipators in this form, I have something imaginary here. Well, I also have, and this is again the equations of motion for average values coming from this master equation. I also have terms that look like Ising interactions, right? X1 and X2 are kind of processing in what looks like a Z magnetic field. And the Z magnetic field that qubit 1 sees is controlled by qubit 2 and vice versa. But what's different, look at these signs. If this interaction came from a Hamiltonian, those signs have to be the same. This funny interaction, it's as though qubit 1 and qubit 2 sees a different sign of the Ising interaction. So answer number 1, what exactly is going on with these funny master equations? Why are we getting entanglement generation? The bath is mediating an interaction between the qubits. It's a funny kind of interaction. It's the dissipative version or the non-reciprocal version of an Ising interaction. Okay, and there's a huge story I could tell you about how many people are excited about non-Hermitian dynamics and non-reciprocal dynamics in quantum systems. This is a sort of funny additional entry in the kind of non-Hermitian interactions we can have. Okay, what's a more microscopic way of thinking about what's going on? So imagine I really started with some microscopic description of the bath. I derived this master equation the way the textbooks tell me to do it, right? So I assume a weak coupling to the bath. I basically do perturbation theory. So those textbooks would tell me, well, look, each qubit is coupled to its own bath operator, right? And we'll think of those as magnetic field, B1, B2, B3, B4, B5, whatever. And to understand these coefficients here, I need to actually understand correlation functions of these bath operators. And I guess I lied. I said I wasn't going to talk about Green's functions. Okay, we'll call these susceptibilities. So the question is, what are the microscopic properties of the bath encoded in the correlation functions of these bath operators that make V complex? Okay, so here is my one Green's function slide. So what do we need to think about? We need to think about quantities that I would call bath susceptibilities, right? If you want, this is a retarded Green's function. So this quantity here, which is indexed by two qubit indices, J and M, right? So maybe 1 and 5. It's the commutator of these two bath operators, right? The coupled to those two qubits. This really tells me, again, if I'm thinking about, I don't know, chi 1, 5, right? If I drive the bath, right, through this operator B5, how much does the average value of B1 change? Okay, so it's a response function, okay? And so now what determines this V being imaginary? Again, doing the standard textbook derivation of a Markovian master equation. It's the fact that these two zero frequency susceptibilities, how does M influence J versus how does J influence M? They're not the same. So as soon as you have an asymmetry there, right, this V is going to be complex. So what does that mean? And what does it take to have those two influences be different? In general, you need broken time reversal symmetry. Okay, so, and again, our paper goes through this in more detail. If your bath has time reversal symmetry, right, then you can prove that these two things have to be the same. V cannot be complex. This dephasing dynamics cannot generate entanglement. If you have the typical messy situation we have in a lot of experiments, there are magnetic fields, there might be fluxes in the system, you don't have time reversal symmetry, well then, in general, there's nothing that guarantees this right-hand side is 0. These V's need to be non-zero. So here's like a bit of a surprising connection. This original question, can this correlated dephasing dynamics be truly quantum, can be different from what you get from just driving with correlated classical noise? The answer seems to have to do with whether the underlying bath, quantum bath, has time reversal symmetry or not. Okay, so if that wasn't confusing enough, let me give you a third way of thinking what's going on, right? And we still had another puzzle I haven't addressed. If these V's are complex, it's not classical noise, maybe we get entanglement, maybe we don't get entanglement. So which is which, right? How else can we think about it? Well, here's a simple example, right? Again, just with 3 qubits of this style of master equation. So a single jump operator, qubit 1, qubit 2, qubit 3, I have this imaginary coefficient here. Lambda is something real. So it turns out there's another really nice, beautiful way of thinking about this dynamics. It has nothing to do with some microscopic, bath. It has to do with the kind of unconditional dynamics you would get if you measured some of the qubits, use that information to then drive some of the other qubits. Okay, so I could imagine a situation where, again, just as a way to sort of understand what's going on, I'm doing sort of measurement and feed forward. So imagine I measure qubits 1 and 2. So I measure the sum of their sigma z's, right? I do that continuously and weekly. So I have some measurement record, I don't know, some photocurrent or some voltage, right? That's a function of time that is sort of letting me estimate what these things are doing. And then I use that measurement record to actually drive qubit 3, right? So this is my feed forward part. So through the measurement, I'm kind of imposing an interaction between qubit 1 and 2 and qubit 3. And then I could imagine doing the same thing in reverse, right? I could imagine another one of these measurement and feed forward loops where now this observer is measuring qubit 3's Z value. They're using that information to drive both qubit 1 and 2. Okay, so it turns out to the standard theory of, weak continuous measurement, this measurement-induced evolution with the feed forward, when you average over all the different measurement outcomes, it's completely equivalent to this master equation. Okay, so it's another way of thinking about this. And this now actually gives us a way of also thinking about this general master equation. So first of all, if V is real, right, if all the coefficients here were real, there was no imaginary part, that was almost like you're having the measurements part of this little cartoon, but you're not doing the feed forward at all. Okay, and so if I'm just measuring a bunch of systems and not doing anything with the information I get, that's not going to generate entanglement, right? If I now do the feed forward, so if I have this sort of evolution, well, if I think about qubit 1 and 2 being here and qubit 3 being over here, right? This is an example of an LOCC type protocol, right? I'm doing something locally over here. I'm using classical communication to sort of do something based on the information I got here on qubit 3. So this sort of protocol can never entangle qubit 1 plus 2 with 3. However, if I ask, is qubit 1 entangled with the joint state of qubit 2 and 3? Well, now with respect to that bipartition, I'm doing something non-local. Okay, so this lets you understand why are we sometimes getting entanglement from these sorts of master equations. We can understand it in terms of you're doing some sort of measurement and feed forward. There's a non-local aspect to the measurement. So here you're measuring both 1 and 2. That is enough of a resource to generate entanglement. Okay, so hopefully if you didn't like one of those 3 ways of thinking about it, hopefully one of the other ways gives you a nice way of thinking about this dynamics. The upshot is we have a way of connecting why can this V be imaginary to the microscopic properties of the bath. Why do imaginary V's sometimes give us entanglement, sometimes not? We can connect that to this measurement and feed forward picture. Okay.
Gosh, there's a question from Luke.
Sure. Yeah.
Question from Luke is from the microscopic derivation, what do the Lamb shifts look like in combination with a dissipative interaction? Do they give a completely directional or non-reciprocal interaction?
Yeah, perfect. So if we go back to this microscopic picture, everything that I've been focusing on is when I start with some bath, right, and I kind of eliminate it and I get a master equation, I'm only interested in the dissipative parts, right? I've thrown away the fact, what Luke refers to is typically as well, when you integrate out the bath will generate a new Hamiltonian, right, for your qubits, right? And people call these Lamb shifts. Why am I throwing that away? Not because it doesn't exist. We know that Hamiltonian interactions can generate entanglement, right? We know that if the bath generated a Hamiltonian that was Z1 times Z5 plus Z2 times Z3, we know those sorts of Hamiltonians can sort of generate entanglement. So what I'm doing here is I'm saying, look, that I know how to understand, check mark, let's throw that away. Let's just focus on the dissipative part of the evolution, right? And ask, does that dissipative part of the evolution have some surprises? Is this purely dissipative part of the evolution always equivalent to classical noise? Okay, so it's a good question. It's an important question. We're taking the point of view that it's somehow easier to think about what a Hamiltonian does. It was somehow less obvious what this sort of dissipative structure would do. Yeah.
Great, thanks.
Cool. Okay, and so I realize I am, of course, going a bit slower than expected, but that's fine. So I've still told you that, look, sometimes when there's complex entries here, right, we'll get entanglement. Sometimes we won't, right? And if you come to me with some big V matrix, it's going to be a giant pain for me to try to think of it this way and all the ways I could partition it and figure out if it gets entanglement, generates entanglement. We want a nicer way of understanding, does a dissipative dynamics like this generate entanglement? We don't want to just evolve this master equation for all possible initial states. So it turns out there's a really kind of slick way that Alareza and Yushin came up with to sort of answer this question. And it involves a particular measure for mixed state entanglement. Okay, and this is this idea of negativity, right? The Perez-Horodecki condition. So I have this collection of qubits, right? I'm going to partition them into a group A and a group B. I want to know in the mixed state describing these qubits, are the A qubits entangled with the B qubits? Okay, so the nice little, simplified version of this idea of negativity or the Perez-Horodecki condition is, let me do something a little bit weird. Let me take my initial physical state of all the qubits, and let me do a time reversal operation just on the A qubits and not the B qubits. Okay, so more technically, this is what we would call a partial transpose operation. So this operation of doing time reversal on just some of the qubits and not all of them, that's not guaranteed to give me a physical state. So this new object here, right, this partial transpose density matrix, it might not be a physical density matrix. It might have negative eigenvalues. And it turns out that only occurs if our initial state was entangled. Okay, so this is a really useful, easy to compute way to see if our state was entangled. But again, I don't want to know if the state was entangled. I want to know whether this dynamics is entangling or not. If I start with some initial state that's a product state, can this dynamics make it entangled? And so the really nice thing is, again, we can take some bipartition. Some qubits will label A, some qubits will label B. Can we entangle the A's and the B's? So we can construct this partial transpose density matrix, time reverse just the A's. We can write down a master equation for this pseudo density matrix. And that master equation is a pseudo master equation. So there's a modified V matrix. So it looks almost like this equation, but the V matrix is modified. I'm calling V modified here. And now what do we find? We find that sometimes that modified V matrix that's describing the evolution of this object, it has negative eigenvalues. Okay, so sometimes through this procedure, the equation of motion for this partial transpose density matrix can turn good density matrices into bad ones. And that's exactly the case where this dynamics is entangling. So the upshot is there's a very, very simple test for, is my original master equation able to create entanglement? I take this original V, right? I make a modification which corresponds to trying to describe the evolution of this partial time reverse state. If that modified V has negative eigenvalues, aha, my original dynamics could generate entanglement. Okay, and so what can we do with this, right? Let's skip that subtlety. How likely are we to get entanglement, right? Is this like some incredible fine tuning and I'm telling you this giant story that is like statistically really, really unlikely to happen, right? Among all the complex V's matrices you could write down, a set of measure 0 generate entanglement. This would be a pretty boring story if that was the case. So what we looked at was, let's imagine we don't have time reversal symmetry, but we don't know anything else about our bath, right? Let's just take this V matrix to be completely random, right? So we're going to take the V matrix to be constructed from some matrix of like coupling coefficients. So this is telling me my n qubits coupled to n baths. These W's are those kind of coupling coefficients. That's a way of thinking about it. We'll just take those to be complex Gaussian random variables. And so this is a well-known ensemble of random matrices, the complex Genabra ensemble. So let's just, say we have this complex V. If we start drawing matrices from this random ensemble, how likely is it that we generate entanglement? And so this is what this plot is showing you. really focus on the y-axis here, right? Every dot is like a different realization of these random v's. The x-axis here, don't worry about it too much. It's just sort of telling you something about the dispersion of the eigenvalues of this random v. The key thing is, as I go from 4 qubits to 16 to 64, pretty much all the points are in this red region. What is this red region? It means that the minimum eigenvalue of this modified v is negative. It means that we can basically generate entanglement. Okay, so the upshot of this is, if you have enough qubits and you don't have time reversal symmetry, without imposing any other funny special conditions or cooking the books in some way, just take these coefficients to sort of be random, right? Statistically, it is very, very likely that this dynamics will be able to generate entanglement. Statistically, right, you're going to be able to get something that's very different than the effects of correlated classical noise. Okay, so I am at the end almost of part 1 of the talk. I won't go through this. In our paper, we also discuss a protocol for if you're trying to do a kind of noise spectroscopy, you want to try to understand, given my actual dephasing process, do I have these complex Vs? There is a very, very concrete procedure, right, for how to actually extract that. Basically by doing a set of Ramsey experiments, both using states that are 2-qubit superpositions and single-qubit superpositions, right? So there is a direct way to get from experiment all of the information in this V matrix. Okay, so this brings me to the conclusion of part 1, and I think we're down to 4 minutes. I am happy to leave part 2 for, you know, some future time and just take questions, or, you know, I could give a 1-minute description of part 2. I will defer to you, Jens, as you are.
I think, you know, we did start a little bit late, so you can certainly have a couple more minutes, and then we can return to questions. There's one in the chat, but why don't we just give you some space and
sure.
Yep.
Why don't, with this second part, I'm not going to, you know, go through it in all its gory details. I'll just give you a flavor of what the problem is and how we think we've come up with an interesting way of maybe not solving it, but a new way of approaching it. So the second part of the talk is we're down to 1 qubit. We still have correlations, but the correlations are now of the noise at different points in time, right? So we're thinking about non-Markovian noise. Here's our noise. This correlation function is not a delta function in the frequency domain. The noise is not white. That gets back to this question of a density of states or spectral function that is not flat. We're going to focus just on non-Markovian classical noise, like this kind of dephasing noise. We're also going to drive our qubits, though, right? And right away, even though this noise is classical, this is a complicated problem because these two things don't commute. So normally we'd say, oh, look, this noise, it has some correlation time, right? The noise is correlated with itself over some time period. If you want to derive an equation of motion for the density matrix of the qubit, it's going to be some horrid integral differential thing, right? The time derivative of rho at time t will depend on what's happening at an earlier time. So that's a giant pain. There are lots of ways of deriving equations like that. What's a simpler thing you could do? A simpler thing you could do is to cheat, right? You could say, well, look, let's get rid of the drive to begin with. Then this is a pure dephasing process. Imagine this is also Gaussian noise, right? It could still be non-Markovian, but Gaussian. We can solve this exactly, right? So maybe I find solving this exactly that my cubic coherence under this non-Markovian dephasing decays not as an exponential, but as e to the minus t squared, right? Divided by something. So how could I cheat? I could cheat by saying, aha, I can describe this with the Markovian master equation. Rho dot of t depends on rho of t. If I just put in the right form of a time-dependent rate, right? And if all I cared about was I didn't have this term here, if all I cared about was this free induction decay of this coherence, well, this gives me the right answer by construction, right? So that's a much nicer equation. Of course, we knew the answer to get that. The sort of cheating part is to say, well, look, if there was no Rabi drive here, This is just another way of getting the exact answer. Let's just put the Rabi drive back in there and hope for the best, right? And so the good news about this equation is it's simple to simulate, it's local in time, right? The bad news is this is a completely uncontrolled approximation, right? You derive this time-dependent rate, ignoring the driving, you just put the driving back in there and hope for the best. So long story made short, we've come up with a way that we think is conceptually and technically simple that lets you take the spirit of this approximation, but basically get these rates in a way that knows about the driving. Okay, and what we find in general is even in this simple problem of a Rabi-driven qubit in the rotating wave approximation with some non-Markovian classical noise, in general, you get two time-dependent rates, two different dephasing processes that are explicitly time-dependent. And even crazier, one of those rates in general is actually negative. So we call this a pseudo Lindblad master equation because it looks like a Lindblad master equation with the exception that one of these dephasing rates actually becomes negative. And I'll skip the kind of intuition here. Let me just give you an example. This is an example just looking at the effects of classical 1/f dephasing noise on a Rabi-driven qubit. You know, these are these negative dephasing rates that we get out, right? You can barely make out some dashed curve here. That's coming from something that's numerically exact. Those negative dephasing rates are even there in the full evolution. The real take-home message is maybe this. So this is some measure of our approximation error as a function of time. This is that naive way of getting a time-dependent rate where you do something that's not kosher and you just hope for the best. This is our new approach. You're seeing an order of magnitude improvement in the approximation error, right? So this is something we're excited about. This is maybe the opportunity. We hope that this is a really useful tool for looking at non-Markovian noise in a lot of different settings. Okay, so I am definitely over time. Hopefully give you a flavor, more of the first story than the second, taste of the second story of, yeah, why correlated noise can be surprising, can be interesting, and can be relevant. And so with that, I will stop. Thank you.
Thank you so much, Ash. It's really remarkable how something as simple looking as going from a real matrix to a complex Hermitian one can cause such rich physics in part one. It's really amazing. There is one question already in the chat that came in a couple of moments ago, I believe referred actually to part one of your talk. And the question is, can you tell how much entanglement can be generated using that method in part one? And is there an easier way to tell the power, it says, of the correlated dephasing noise?
Yeah, and so, you know, I guess that's an interesting question. There's a couple of interesting things, right? So even with this correlate, so this is showing you that, you know, statistically, you are likely, if you have enough qubits and you have this kind of random complex V matrix, that you will be able to generate entanglement, right? The first thing I should make very, very clear that this plot also highlights, this is not steady state entanglement, right? So this is not like reservoir engineering. There's some transient period in the dynamics where you started with no entanglement. At very, very long times, you have no entanglement. At some intermediate period, you have entanglement. And so then there's interesting questions that I don't think I at least have complete answers to. I don't know if Alireza and Yushin have made huge progress since the last time I talked to them. There's interesting questions in terms of understanding for a specific realization or in a typical sense, what sets this time scale? What sets the maximum over here? What happens when you go from a 2-level system to a 3-level system to infinite level system, right? So there's a paper that hopefully will be on the archive in the next, you know, I don't want to promise things too soon, in the next month, let's say, where this physics extended to just harmonic oscillators turns out to be really, really rich as well, right? And the upshot is, as you go to a larger and larger local Hilbert space, right, the value of this entanglement and like how long it persists can be sort of pushed to the right and further up more and more and more. right? Whereas it turns out even in the bosonic case, you could really have an entanglement that just keeps growing forever as a function of time. So it's a really interesting question. I don't think we really have the full answers. And I should really stress here too, if your goal is to engineer a bunch of qubits, I am not suggesting that this is the best way of doing it, right? What I'm suggesting is even in this simple limit where you thought you're dephasing, maybe it's correlated, maybe it's Markovian, and you want to fight it somehow, just assuming it's the same as classical noise, you could be missing something really important, right? Even if you think the noise is completely Markovian.
Thank you. I'm waiting for more questions, but in the meantime, I did have one which is closely related to this point in the talk. So this condition named after Paris and Horodecki, it's a one-way street, right? It's sufficient but not necessary. Is there something that you can say about the possibility of having, I guess, positive eigenvalues but still generating entanglement?
Yeah. So you know, we can't rule out the fact that, look in these diagrams here, that look, some of these points in this safe blue region, there still might be entanglement generation going on that doesn't violate this Perez-Horodecki condition, that is basically an example of what people would call bound entanglement, right? We have not spent a lot of time thinking or kind of worrying about that. Again, the justification being is if I have enough qubits, right, and in this random setting, even if I don't worry about the bound entanglement, I have some entanglement going on. Yeah, it's not something that we've really spent a huge amount of time thinking about, you know, and yeah, I would, you know, maybe this is risking, you know, someone getting angry. I've never been, yeah, in terms of bound entanglement being interesting and something we should spend a lot of time trying to understand, I've never seen a great sort of motivation for that, right? So having a, you know, having an entanglement of formation, but no distillable entanglement, usually that doesn't sound like so useful to me, but it's a good point though, right? Some of these points up here, maybe there's still generation of sort of bound entanglement. Yeah.
Thank you. Are there more questions?
I see Ian.
I have a question.
Yeah.
Sorry. So I have actually two many kind of basic questions. So on the question of entanglement dynamics in this time scale over which the system becomes entangled. So generically, you do expect that at long times the entanglement does go to zero. Is that your expectation, or?
Yeah, and the only way out of that is to have an infinite dimensional local Hilbert space, right? So that's something we'll show in this paper on, you know, oscillator or cavity systems. There, it doesn't have to go to zero. But I think anytime you have a finite dimensional local Hilbert space, it will go to zero. I can give you a really, really hand-wavy argument for that. And the hand-wavy argument is, there's this picture for why are we generating entanglement. It's these dissipative Ising interactions that are Bath mediated. These interactions by themselves, right? Hey, look, it's an Ising interaction. It could generate entanglement. These interactions have to come with noise, right? So like it's the, you know, there's no such thing as a non-Hermitian Hamiltonian. There's only like damping terms and a Langevin equation that come with noise. Quantum mechanically, you can't escape fluctuation dissipation. So the argument is that these interactions can generate entanglement. They have to come with noise. There's a minimum amount of noise that they have to come with. If you wait long enough, that noise will eventually kill you. Making that quantitative is sort of I think an interesting challenge, but that's some of the intuition for why if you wait long enough, the entanglement will go away.
I was curious about this equation actually, because there's an operator on the right, but because you took expectation values? So
Yeah, sorry. And also in our dynamics, we could take expectation values, but yeah, these are kind of conserved quantities.
I see.
I should have written, you know, well, if I was being very careful, like the average value would be on the product of those two things. Yeah.
Yeah. So the other question that I had was on this notion of spatial. Usually I kind of tend to think about, you know, some locality or something like, but this V doesn't really necessarily encode in any locality or anything, right? This is just all-to-all interactions.
Well, it could, right? So most of the talk is about there is some n by n matrix V. It has some complex entries. Is it band diagonal? Is it,
Right.
who knows, right?
Right.
The
Yeah.
only place where we really throw away any notion of spatial locality is in this model where we treat the entries of V being completely random. Then there's no notion that one qubit is somehow closer to another. So you could imagine a more constrained model for V, where you maybe still allow for some randomness, but you say that, look, whatever correlations exist, look, maybe my qubits live in 1D, qubit J is going to be correlated, the noise it sees, with J minus 1 and J plus 1, right? And that's also an interesting question if you put that in there.
Right.
How much does it change these sorts of results here?
Right. Right. I see. Okay, thank you.
All right, more interesting questions. First one from Saeed, who thanks you for the excellent talk, and then asks, in part 1, is there any indication of the partition size of the generated entanglement? Also, is there any information in the eigenvectors of your V mod as opposed to the sign of the eigenvalues?
Yeah, and so that's another important thing I realized I didn't state. When I calculated, when I showed these sort of plots here and characterized entanglement, obviously if I have 64 qubits, there are many bipartitions I could pick. We always singled out one qubit and called it system A, and we called the other big N minus 1 qubit system B, right? So now if we looked at different bipartitions, right, one could ask, how different do these plots look like? I think I'm remembering correctly that we also looked at symmetric bipartitions where A and B had equal numbers of qubit, and there was a qualitatively similar kind of picture. In terms of the eigenvectors, right, I think the eigenvectors are going to, give you information on, in terms of the correlation structure, right, which qubits tend to be correlated with which other qubits. So if you wanted to know more than just, can I generate entanglement, but what is the nature of that entanglement, right? I think then delving into the properties of those eigenvectors more would be really instructive. And, there's a long list of things to do. One thing is there's an enormous mathematics and mathematical physics community that a lot of questions about standard random matrices ensembles, someone has written it down somewhere in a math journal. So there's a question of, could we harness some of that existing knowledge and really apply it to sort of say even more precise things about entanglement generation in this setting? Yeah, it's a good question. We haven't really milked whatever structure there is in those eigenvectors. Yeah.
Great. Sophia has a question for part 2. Under what conditions can you represent the dissipative dynamics through a time-dependent gamma and local in row equations? Is there a way to derive that function? And does the derivation assume the system is not driven? And she remarks in parentheses, I'd assume so.
Yeah, so the full, is there a statement here somewhere? Yeah, so, okay, the slides don't really give you a lot on the technique. The technique is really based on, there are many, many versions of using cumulant expansions for sort of matrix stochastic differential equations. And these really have a long history. So we're really using some of that machinery, right, to sort of generate these master equations. So based on a cumulant expansion, so ultimately that involves a kind of small noise. I hesitate to call it short time expansion, but definitely not infinite time expansion. In terms of not including the driving, we include the driving completely. So the way that the derivation works is, and again here, the Rabi driving is in sort of the rotating wave approximation, so it's easy to deal with. But we work in an interaction picture that includes all of the effects of the driving. And then the cumulant expansion is done on some level in the size of the noise. And so that's actually one of the, let me just quickly flash a result. So this is for like the simplest, most non-Markovian kind of noise, where the correlation time is infinite, so quasi-static noise. And again, the naive approach and this improved approach, there's a huge, huge difference. What's going on these dephasing rates know about the dynamical decoupling that's sort of intrinsic to this kind of system, right? So these rates definitely know about the effects of the driving. This is generally a difficult problem, like dissipative dynamics and driving. What makes it easier for us is this noise is completely classical, right? But even in that limit, we can sort of say a lot. We think that maybe there are non-perturbative things to do. But yeah, I didn't want to give the impression that we just wrote down some rates. There is a systematic way of deriving these things. The derivation also lets you understand where it breaks down. Yeah.
Sophia says, thanks. By the way, Ian has been trying to ask a question for a while. I thought that he just didn't remember to lower his hand, or was there a second question?
No, the hand got stuck there, so
Got
just
it.
figured out how to
Zoom
unstuck
problem.
it.
Yeah.
All right, last chance. Any final questions for Ash? Okay, if that's not the case, then thank you again, Ash. A really wonderful talk. Always great to see you. Thank you.
Thank you, everyone. Yeah. Bye.